Thank you. So, and thank you for putting together this very timely workshop. So I'm going to tell you a bit about the Qudit activities in Innsbruck. A lot of it actually happening in this experiment here. So that's a view into one of our Qudit quantum computers. You see the ion trap hanging from the top. And here in the center, in this little slit, we have a chain of individual calcium ions. So in our case, this is calcium-40, which is kind of one of the simplest ions. You'll hear tomorrow about a more interesting ion. But what's important and what's kind of similar for all of them is you need a long-lived transition where you can store some information, and you need a short-lived transition where you can read out the information, right? That's kind of the structure. The theorists can stop here. For the rest, we look a bit more in detail, and we see that already in our simplest ion here, which has no nuclear spin, so just Zeeman splitting, you get 2 ground states and 6 excited states. Yeah, so we can very conveniently encode a qudit here. The thing is coupled, so the ions are coupled to each other because they're charged, so they're in this chain. They repel each other, so you have a harmonic oscillator degree of freedom in this trap. Okay? And this is going to be the bus that we use to mediate the interactions. So the way this looks like, you have an atom, you have a harmonic oscillator. We all know this. You get a coupled system. You get all kinds of transitions in there. And in particular, you have your carrier transitions, which just change the internal state of the ion. And you have the sidebands, which couple the spin to the motion and then can be used to create entanglement. That's how it looks like in the end. That's kind of the classic Innsbruck-style ion trap with these blades where you apply radio frequency fields to trap the ions. They line up in a linear chain. You have lots of optical axes. So you have your red laser beams that do the computing and the blue laser beams that do the cooling and readout. And in the end, you get a picture like this on the camera where when the ion is in the ground state, it's bright. When it's in the excited state, it's dark. That way you can read it out in the end. Okay, so this is what we see in the lab, actually. All right. I quickly review the kind of operations we use. Everything is very similar to what we heard already, but just so we're all on the same page. Right, so the basic thing you can do, of course, is you pick one of these transitions between the ground state and the excited state. You drive that resonantly. You get rotations around the XY plane of your Bloch sphere. You can do that with a global laser beam, which is kind of interesting for analog simulation applications where all the ions are doing the same thing independently of each other. Or you have addressed laser beams if you want to do more computation. Right, you can detune your laser from that transition, which means you don't get population exchange anymore, but you still have, you change the energy structure, which means you get a Stark shift. Yeah. It works again. Now, as we've seen already with the other talks, you can benchmark these things. Now, the good thing is, whenever you have any kind of connected structure, you can do arbitrary operations. And we do it the way we just heard. We decompose everything into these 2-level couplings. Yeah, then you benchmark this with your randomized benchmarking. And you see pictures like this, where the slope of these lines is the average fidelity of the Clifford gates. You see that it gets worse with dimension, but it gets worse in exactly the right way, namely quadratically. And if you look at the error rate per laser pulse, you see this is actually constant, which means we're not losing anything. We have control over all these additional levels. Okay. As we just heard in the previous talk, there are other ways to do this with multi-tone drives. So far, we're a bit too lazy for that because it's not really a limiting factor. The more interesting thing, of course, is entanglement. And here, we already heard from Pavel in the very first talk that things change when you go to qudits. One thing that changes, so one thing that stays the same, which is good, is you just need a single entangling gate. We heard that, right? Something that changes is that a lot of the structures we're used to don't apply anymore, particularly these equivalences that we know between a C0 gate and a CZ gate and a Mermer-Sørensen gate that we like to use. This last one does not hold when you have that Mermer-Sørensen gate embedded in a larger Hilbert space. It's a bit annoying, but we can get around this. The other thing that's important is that, of course, you have qualitatively different entanglement structures in that qudit. Big playground to explore. And here, already in the simplest system, so you take 2 qudits, you can make entanglement that looks like this, right? So it's essentially qubit entanglement embedded in the larger Hilbert space. Or you can have genuine qudit entanglement. Each of those is fine for universal computation, but depending on the application, one might be more efficient than the other. And so really we want to have both of those to be able to tailor the platform to the applications we want to look at. And quite intuitively, we can achieve qubit entanglement by driving one of these transitions in our ion with a slightly modified Mermer-Sørensen gate. That gives us the qubit entanglement. We see again, like before, we can do this, we can control all the other states, so we don't have any drop in fidelity when we do that. If you want genuine qubit entanglement, one way to get there is you drive far off resonant, so that you're actually coupling to the whole ground state manifold versus excited state manifold, and that gives you directly qubit entanglement. Nice thing about this gate is that it only has a single control parameter independent of the dimension. So for the people in the lab, it's very convenient. There's also another nice generalization of the MS gate to Qudits coming out of IQC, but you might hear about that tomorrow, I don't know, so I won't say anything there. One thing I still want to mention, we still want another gate because we never have enough, and that's a mixed dimensional gate, because we find that in many applications, and you'll see that later, we actually deal with mixed dimensional systems, so we need something that supports that naturally. And here we go in some sense back to the roots. We use our motional mode as a bus. So you take a control qubit, pick a state. For that state, you inject the phonon into the motional mode. And if the phonon is there, you do whatever you want on your target ion. So that's natively a mixed dimensional gate because it doesn't care about the dimension of the ions at all. And you can do arbitrary controlled unitaries that way. Good. Last thing to say about the measurement, because I said before the measurement is a bright-dark distinction, which is kind of a binary thing, and also means that we can't distinguish our two ground states down there. So in order to do the measurement, we actually need to park the information up in the excited states, and that's the reason why I will talk about a 7-dimensional Hilbert space, although we have 8 states, because one of them we need to keep free for the readout. But then you can just take a picture with your camera, and you see if it's bright, it was 0. If it's dark, it's somewhere in the excited states, but it was not perturbed by the measurement because no photons are scattered. So you can just do your mid-circuit measurements and keep going until like you swap the states, measure again, swap the states, measure again, until you identified all these states. Now that gives you kind of a linear overhead, but that's all not a limiting factor at this stage. Okay. So that's all I wanted to say about the platform. So you have your arbitrary local gates, you have qubit entanglement, and mixed dimensional entangling gates, and maybe some more if you have good ideas. There's lots to play with. In terms of how the experiments look like, it's not like this anymore. This we just show to scare the theorists. That's how it used to be. Nowadays, everything can be nicely integrated into these 19-inch rack systems. So you have essentially one rack which contains all the optics and lasers and so on, and you have another rack which contains the ion trap and the electronics and control for that. This is how a newer version of that thing looks like. Good. That's what I wanted to say to the experiment. Now let's talk some applications. And I like to group this in two categories, and we heard about these things already at the workshop. One that I call qudit-enhanced information processing. So you take your standard qubit computer and you use the control over the qudit Hilbert space to make things better. And the other thing is native qudit information processing, where you're trying to solve a qudit problem using a qudit hardware. So on the first thing, there are various degrees of complexity you can look at. Some things that have been done for a while is spectroscopic decoupling. So you can say you have a cache memory within each ion, and you can use that to store information, park it there during certain interactions where you want to decouple your ions from interactions. And that was used, for example, in this first quantum simulation of quantum electrodynamics that we already heard about. Also in the first demonstrations of quantum error correction on the ion trap systems, that was very useful. Also for nowadays, for things like mid-circuit measurements, you need to park information there somewhere to protect it from the measurement and so on. Other things you can do is you can induce controlled dissipation. That's very nice. Was used a while ago to study open quantum systems, and you can really design whatever dissipation jump operators you want. That's very nice. You can reset qubits, of course, that's on the one hand important for error correction. On the other hand, you can do nice things like create short-range entangled state on the fly. So for example, cluster states for sampling problems or measurement-based computing. You can just, once you're done with the qubits, you measure them, you reset them, you attach them in the end, and you can grow your state much larger than your actual register size. And the last thing I want to mention is crosstalk suppression. Crosstalk errors are something that are a nuisance and that are quite significant often. Now we can recognize we have a large Hilbert space, and I just briefly flashed this experiment where we used this. This was a simulation of the SSH model with qubits. Using these blue sideband gates where you use only local operations, directly addressing the blue sideband. And so it doesn't matter where your ion is encoded. And in particular, you can now go and say, I encode odd sides and even sides of my chain in different parts of the Hilbert space, which means you're essentially free of crosstalk because the neighbor is not resonant with your drive anymore. And we tried this out here and essentially got a 40% reduction in the error here, as you see in these tomography pictures, just by changing the encoding a little bit and recognizing we have more Hilbert space than just a qubit. Good. That's the basics. Now, something else that is quite neat and something that's also important is estimating properties of your quantum states. And we all learn essentially in high school that if you want to characterize a quantum system, you measure your 3 Pauli directions, right? And then you have all the information. If it's not 1 qubit but more, you do this for all the qubits. So you have your 3 to the power of n measurements. Once you have that, you can do the tomography. You can get everything you want about this quantum system. Also, if you don't like tomography for applications like variational quantum simulation, where you need to evaluate lots of candidate states and measure the Hamiltonian or Hamiltonian squared, you often have to measure a lot of different Pauli strings and so on. So we want to do this efficiently. Now, this is not a great way because for tomography it scales exponentially, and for other things it also tends to be a bit of a pain. But the reason is because this is really not the way to measure a qubit. And we've known this for a while, that actually you should be doing this kind of measurement. So this is called a symmetric informationally complete POVM. That is the optimal measurement for a qubit. And you can also kind of see why. So it has 4 outcomes, which is the minimum you need to characterize a qubit. They are equally spaced in your Bloch sphere. So in that sense, it is optimal in terms of information gain. The problem is you also see this is not a projective measurement. These vectors here are not orthogonal, so you can't actually measure that in a qubit system. But you can measure it if you can make your Hilbert space larger, because we know that any non-projective measurement turns projective in a large enough Hilbert space. And this is now something we can do quite easily. So say you have a register of n qubits, you do some computation, then you want to characterize it. So at the last step, you increase your Hilbert space dimension from 2 to 4, which is just a bunch of local operations, so this is essentially for free. And then you can do this in such a way that the 4 states of your Hilbert space encode the 4 outcomes of your POVM. What that now means is you have, with essentially 0 overhead on the experimental side, you now get full information about your quantum state in every single shot. So full tomographic information. Or in other words, you went from 3 to the power of n measurements to 1, independent of system size. Now this is very convenient. And it's particularly convenient if you combine this with another technique that was developed recently, which is classical shadow estimation. That's usually based on randomized measurements, randomized Pauli measurements, which is nice in theory, but in the experiment that's a huge pain because changing your setting every time is very annoying and time-consuming. Here you get this all for free because your measurement already contains the full information, so the randomization that you need for shadows is intrinsic to your measurement design. So putting that all together, you see, again, for like a variational simulation example that was done in Innsbruck a while ago, the typical scheme would require 3 n measurements. Now that's linear, but linear is still a pain if you want to scale up your system. With the shadow estimation, you get this down to a logarithmic scaling, which is the closest you can get really to constant. So that's a huge advantage here. We tried something else. We tried to do tomography with this thing on an 8 qubit state here. In the past, that used to take about a day measurement on our device and a week of maximum likelihood reconstruction. Now you can do this in real time because the post-processing is very efficient, and you have a single measurement setting. So you just start the thing, you watch how all the quantities of interest converge, and once they're converged, you just stop it and you're done. And you see in particular for things like entanglement characterization here with these Rainy entropies, it converges really quickly. It actually converges faster than just measuring a single shot in every Pauli basis you would need for a standard Pauli tomography. So that makes a big difference in the lab. All of this can be done in an online fashion. So you get a new measurement, you update your estimates in real time, up to about 20 qubits, then my laptop doesn't want anymore. If you have a stronger computer, you can push this a bit further. But this turns out to be a very useful technique. And you can pick whatever you want to estimate. If you estimate easier quantities, then the post-processing gets more efficient. You can push this to hundreds of qubits as well. Okay. All right. Now, so far for the Qudit enhanced things, there's lots more that could be done, but as kind of a general theme, right, you get better measurements, you get semi-classical control, you can do certain error suppression techniques. There's lots of ways in which just having access and control of this Qudit Hilbert space can help you in all the standard qubit applications. Good, but now we talk about native Qudit information processing. So we want to solve Qudit problems on Qudit hardware. And this is where we think that we can get really a speed up compared to standard methods. And I want to start with something well known, which is a spin-1 Heisenberg chain. This is an important model because this is kind of what started the field of topological states of matter, symmetry-protected topological states. It was recognized by Duncan Haldane that there is a fundamental difference in this Heisenberg model between spin half and half integer spin and integer spin chains, where the half integer are essentially trivial and the integer spin chains show topological behavior. And this is interesting because this is really a fundamental difference between a qubit and something larger than a qubit. So this is what we want to study. But we're not going to do the Haldane directly. We're looking at what's called the AKLT model. That's kind of a slight perturbation of the Haldane Hamiltonian. You see this here with some quadratic disturbance. But it's in the same phase. And so it shares all the same properties. And it's interesting because it has this nice interpretation where you take each spin 1, you split it up, so you represent it as 2 spin half, and then you project it onto spin 0 subspaces in the middle. So it's kind of a convoluted constructions, not particularly useful for our purpose. But what's interesting here is you directly see that on the edge, if you have open boundary conditions, on the edge there is a spin half degree of freedom left over. And this is really what you see in this model. One of the interesting aspects is that you have a fundamentally spin 1 system, but you have a spin half degree of freedom sitting on the edges. So that's called spin fractionalization. Now this is what we want to see. Now the nice thing about this model is it's a short-range correlated thing, so you can essentially construct this as a matrix product state by sequentially coupling your spin 1 systems to an ancilla. So it's a scalable way of creating these states and also other MPS type states. Now once you create this, you can first look at your correlation length, and you see the correlation length is very short, as you would expect. So essentially, these edge modes are localized on the outermost 2 spin 1s. And you can then construct an SU2 algebra on the edge, look at these 2 spin 1s, so a 9-dimensional Hilbert space, and you see you have an SU2 algebra, so you have a 2-dimensional degree of freedom within that 9-dimensional space. You can drive Rabi flops on this and verify that you really have this qubit sitting there on the edge. Now in these topological systems, you also have correspondence between what happens in the bulk of the system and what happens on the edge. So you can do the same thing by driving bulk rotations, and you get the same kind of Rabi flops on the edge degrees of freedom by driving bulk rotations. And these are global SO3 rotations that the system is here protected against. you still get the Rabi flops because you're permuting within the ground state subspace of that Hamiltonian. Right? Another nice thing here is if we increase the system size, you see that actually the contrast of these Rabi oscillations is constant. From 2 to 4 at least. From 4 to 5 it drops a bit because we added more ions to the trap, which lowers the gate fidelity a little bit. But otherwise you see it doesn't depend on the string length, which is a very nice feature of this system. Okay, so much for that. Now we go to the last part here, and I think I still have a bit of time, which is gauge theory simulations. And we heard about that already in the morning. And so I will just talk about this rather superficially, but if you want all the juicy details, there is a poster by Mike that you can look at later. So I'm not going to motivate gauge theories. We heard that. I mean, there are problems in there where we are fairly certain that we won't be able to solve them with classical computers, which is why we want to do this with quantum computers. And the simplest model here is quantum electrodynamics. So you have charged particles and antiparticles. They interact via a electromagnetic field. They can annihilate, and they can spontaneously be created out of the background field. Okay, these are the effects that you want to see. And now starting with the simplest example of quantum electrodynamics is 1D. Here you immediately realize that you don't actually need the gauge fields, right? Because if you put charges on a line, the electric field is completely determined by the way you arrange the charges. And realizing this is what allowed this early simulation of 1D QED done in Innsbruck, where here what was done is prepare the vacuum state, which is not actually the ground state of your model, let it evolve over time, and see the creation of particle-antiparticle pairs out of that vacuum. And you see how that changes with the mass of these particles. The heavier they are, the less likely it is to create pairs because it's more expensive. And then you get some oscillations because pairs are created, they annihilate again, and you get this interesting dynamics, which is really beautifully captured by the experiment. So that's a nice first step, but you see the gauge fields here are not really relevant. There's not any dynamics in the gauge fields, and more importantly, there are no magnetic fields, because magnetic fields need loops somewhere. Right? And in 1D, you don't have loops. So really, this is not real-world physics. And if you want to do real-world physics, we need to go to 2D and then 3D. But 2D and 3D are actually quite similar. So we go to a lattice. Again, like before, we put our matter on the sides of this lattice. We put the gauge fields on the links. We now need to treat the gauge fields explicitly because they're not fully determined by the matter configuration, which means you have this infinite dimensional system to deal with. And the smallest truncation of this you can do, you need to truncate somewhere. The smallest truncation you can do is dimension 3, because you need a gauge field pointing up or down, or it can be 0. And better you want dimension 5 for your truncation, and depending on the physics you're studying, it might be more or less that is needed. Right, so putting together our list of requirements, this is how I imagine gauge theory simulation. You have some low-dimensional things, which are your matter fields. You have some high-dimensional things, which are your gauge fields. This is something we can do with these mixed-dimensional entangling gates. You need 3D geometry eventually. This is also something we can do because we have this all-to-all connectivity in the ion trap system, so that's not a problem. Now let's go. That's the Hamiltonian we look at. It's fairly simple. If you want to know what's behind all these H's, you have to ask our colleagues here. Now, essentially, it's an electric field contribution and a magnetic field contribution. They scale in opposite ways with the coupling strength of the model, which is this G. You have a particle mass term, and you have this kinetic energy term, which is the coupling between the particles and the field. So this is where the particle pairs are created. And then you have to satisfy the Gauss law on each of these vertices to make sure that the field configuration matches the charge configuration, right? Good. The smallest building block for this is now a single plaquette. So you have 4 matter sites and 1 gauge field. We encode this in our trapped ion system here, 1 qubit, 4 qubits in this case. And the goal is now to prepare the ground state of that model for different values of the coupling strength. We do this with a variational method. We heard about that already, so I don't have to say much. This is how the circuit looks like. You see this is kind of inspired by the physics. You have the blue blocks, which are pair creation terms in a sense, and you have the red ones, which are changes in the gauge field depending on the state of the matter fields. Good, so we do this. We run our variation optimization to find the ground state of the model for different values of G, actually all done in parallel. You can bother Mike if you're interested. And once we find the ground state for different values of G, we look at this plaquette expectation value. Now the plaquette expectation value is important because this is now really your 2D quantity, right? This is the thing that doesn't exist in a 1D model. And it's essentially the magnetic field flowing through that plaquette. So looking at this, you can identify 3 interesting regimes. On the left side, you have the strong coupling regime, and you can thank the particle physicists for putting that on the left side of the plot. But essentially here, everything is electric field dominated. So it's very expensive to create particle pairs, which means essentially nothing is happening there. On the right side, you have the weak coupling regime, which is magnetic field dominated. So you have a magnetic field, but the magnetic field dominates the whole thing, so there is no entanglement left with the matter. Again, boring. The interesting part is here in the intermediate regime, where you really have all terms roughly equal magnitude. So you have this competition between the field terms and the matter terms. And you then get dynamic and magnetic fields. You get entanglement between matter and gauge fields. So this is where the interesting stuff happens. And essentially the way you see this is the slope changes. The stronger the interaction between matter and fields, the shallower that slope becomes. Good, and we also added here a noise model, so you see it's fairly well understood how the system behaves, and that all matches very nicely. Now, before I talked about truncating in dimension 3 and dimension 5, so we want to look at what that does by now studying just a pure gauge theory. That's interesting if you care about things like the running coupling of these theories. That's where you want to look at pure gauge theories. So you only have these first 2 terms of the Hamiltonian now. And here you see when you are again in the strong coupling regime, you're electric field dominated, so you can truncate very hard and you don't have to worry about anything. But the further you go to the weak coupling regime, the more of these electric field states are getting populated and your truncation essentially explodes. But thanks to our friends from IQC, there is a solution for this, which is changing to a different basis, namely the magnetic field basis, which is done by a Fourier transform. And then here again, you're dominated by the magnetic field, so you can truncate in the magnetic field basis very well. And then you only have to worry about the intermediate regime where things can get a bit out of hand. So to look at this, we do something very similar to before. We now take a pure gauge plaquette, which means we need to keep track of 3 gauge fields. That's how the circuit looks like. And again, variationally prepare the ground state of this system, and you get something that looks like this. So looking at this in more detail, this is again the plaquette expectation value, so the magnetic field in this system. You see on the left side of the plot the red curves, which are the electric field representation, very accurately track the behavior of the system. On the right side, the blue curves very accurately represent this. In the middle, they diverge. And then you can play with scaling of your truncation. And you see here, as we go from the dimension 3 to dimension 5 truncation, these curves approach each other. And if you go another step further, they would soon touch, and then you have the match that you want, and you can continuously scan that whole parameter regime. All right. Because the question came up, I say one thing about efficiency of this. So this is not only very natural for the problem, but it's also very natural for the hardware. As you've seen with these mixed dimensional gates, this is exactly what happens here. And you see already in the case where you have gauge fields and matter, where the matter is qubits, so you really only have 1 qubit in there, you're already gaining about a factor of 5 in gate count. And if you go to the pure gauge theory, where the qubits can really play out their strength, you're gaining over an order of magnitude in gate count, just by going to this qudit representation. All right, with that, I'm wrapping up already. So I showed you how we do a universal computation here, and that this is very nice for quantum simulation applications. What we really need right now is much more algorithm development. There's some work, as we've seen from Pavel and others. There's more work needed on compilers. Also here, a bit of initial steps that you can look at. And we always like to play with these things. So if you want any gates that we don't have yet, just let us know. These are the Antrappers in Innsbruck. Those are the people that were involved in the Qudit work. And there's always space for more. So if you're interested, just come talk to me. Thank you.